We're going to do a few problems from the 2.6 homework involving center of mass in the one-dimensional case when you're given a density function. So our goal here is to evaluate these two integrals, the first one being the total moment and the second one being the mass, and then forming this quotient, and that is going to give us our center of mass. So, for example, with 261, we have a row function of x squared. So we want to find x bar, which is going to be the integral. We're integrating from 0 to L, x times x squared dx, right? We're doing this right here, where x squared is row of x. And in the bottom, we're going to integrate from 0 to L just our density function, which is x squared dx. And now we'll go ahead and simplify that and integrate. And there you have it. Let's look at 263. It's very similar. We've got x bar, which is going to be the integral, in this case, from 0 to pi of x sine x dx over the integral from 0 to pi of sine x dx. The denominator integrates pretty easily. So does the numerator. We could just do integration by parts there, right? So if we let x be u, doing the tabular method, we take repeated derivatives to get down to there, and then we take repeated antiderivatives to get something like this. Then we'll multiply here, positive product, there, negative product. And so our numerator is going to become negative x cosine x plus sine x, right? So that's a negative and a negative. And then what do we have after that? We're integrating that, or we're evaluating that from 0 to pi. And then on the bottom, we'll have negative cosine x, also evaluated from 0 to pi. So our numerator becomes negative pi cosine pi plus sine pi, which is 0, minus. And then we have 0 times cosine of 0, which will be 0, and then sine of 0, which is 0. And then in the bottom, we're going to have, I'm going to put the negative on the outside, so we have cosine of pi minus cosine of 0. So cosine of pi is negative 1, so on top we just get a pi. On the bottom, we're going to have the negative of negative 1 minus 1, which is the negative of negative 2, so we get a final result of pi over 2. Continuing on with 265, again, we want x bar, which is going to be the integral from, over here we're going from 0 to 2, and we need x times row of x, which will be x e to the x. Hopefully you're immediately thinking integration by parts there. And in the bottom, we're just integrating e to the x dx like that. So again, tabular method, x1, 0, repeated derivatives, repeated integrals, or antiderivatives, and we're multiplying here and multiplying there. And what do we get? We get x e to the x minus e to the x, evaluated from 0 to 2, and of course the bottom is just e to the x, evaluated from 0 to 2. In the numerator, we're going to have 2e squared minus e squared, minus 0 times e to the 0, minus negative, so we're going to get plus e to the 0, like that. And on the bottom, we have e squared minus e to the 0, which is 1. And that should simplify to give us e squared plus 1 over e squared minus 1. Now looking at 267, we have, again, we're finding x bar, which is going to be the integral from 0 to pi this time of x times x sine x, right? X sine x is our row function, dx, over the integral from 0 to pi of just x sine x dx. Of course, the numerator we can write x squared, so I'll change that. And hopefully we're seeing two integration by parts, right? We've got x squared, repeated derivatives, and sine x, repeated integrals, or antiderivatives. And then we'll have these diagonal multiplications, plus, minus, plus, like that. And on top, we're going to get negative x squared cosine x. And then we'll get plus, because we have negative 2x sine x. And then we'll have plus 2 cosine x. And then on the bottom, we have to do another integration by parts. So we have x, 1, 0, sine x, negative cosine x, negative sine x, multiplying here, multiplying there. We get negative x cosine x plus sine x, evaluated from 0 to pi, evaluated from 0 to pi. You can go ahead and evaluate that one on your own. 269 is done in a similar fashion. And 271, now you're finding the center of mass of a two-dimensional system. And in that case, you can use x bar is equal to 1 over a, integral from a to b, of x f of x dx, and y bar equals 1 over a, integral from a to b of 1/2 f of x quantity squared dx, like that. I would probably just do 271 using these directly instead of trying to use symmetry. I hope that helps.